In 1998, gravity lost the war for the cosmos. For decades, the collective consensus of physics assumed that the expansion of the universe was a finite process. Astronomers believed the relentless pull of matter would eventually rein in the outward movement of galaxies, causing the cosmic expansion to slow, stall, or even collapse. But when Saul Perlmutter, Adam Riess, and Brian Schmidt turned their telescopes toward the furthest reaches of space, the expected deceleration never appeared. The team was hunting for standard candles, the distant thermonuclear screams of Type 1a supernovae. By measuring the brightness of these dying stars, the researchers intended to map the gradual breaking of the universe. However, the data revealed an impossible result. These ancient signals appeared significantly fainter than every model predicted. The light had traveled through a volume of space expanding faster, not slower, than the laws of physics allowed. In that single, staggering moment, the fundamental blueprint of existence shifted. The universe was not slowing down. The universe was accelerating. The revelation represented more than just a minor correction to the cosmological constant. This mathematical term, originally inserted into the equations of general relativity by Albert Einstein, represents the inherent energy density of empty space. For nearly a century, scientists believed this constant was zero or irrelevant. The discovery in 1998 issued a death sentence for that connected cosmos. The accelerating expansion suggests that nearly 70% of the energy density of the universe resides in an invisible, repulsive pressure known as dark energy. As space expands, the density of this dark force remains constant while matter dilutes. This imbalance creates a cosmic event horizon closing in on us, a physical boundary where the fabric of space stretches away faster than light can cross the gap. We are currently residing in a unique temporary window where the history of the Big Bang is still visible across the night sky. But soon, every galaxy beyond our local cluster will be driven outside this horizon, proceeding at speeds exceeding the light limit. The great cosmic web is dissolving. The local group will eventually merge into a single, isolated mass, a lonely island adrift in an infinite, lightless void. We are moving toward a future of absolute, permanent isolation. The official story of a stable, observable universe is a fabrication of our current privileged perspective. We must look beneath the smooth surface of the cosmological constant to understand the violent tension within the vacuum of space. Hidden layers of physics suggest that our era of astronomical abundance is a fleeting anomaly. The universe is not just expanding, the universe is actively erasing the history of the cosmos. This process represents an ultimate cosmic hard drive failure, where the backup data never existed and the disk is being physically shredded by the expansion of the vacuum. We will uncover the mechanisms of the de sitter horizon, the boundary beyond which cosmic events become forever unobservable, and the strange nature of phantom energy, a theoretical force that grows stronger as space expands. We will connect the faint light of distant supernovae to the ultimate dissolution of atomic matter. The evidence indicates that the time remaining to observe the truth is expiring. Over the course of this journey, we will descend through the chapters of cosmic erasure. Our path begins by revisiting the 1998 revelation shattering the standard model of gravity. This model, governed by general relativity, describes how matter and energy warp the fabric of space and time to create the force we feel as gravity. From there, we must confront the terrifying discrepancy of the vacuum energy problem, a gap where theoretical predictions exceed observed values by 120 orders of magnitude. We will analyze the competition between quintessence, a theoretical, dynamic form of dark energy, and the static cosmological constant, tracing the receding horizons of the Great Isolation. Our adventure will span a timeline of the next 100 billion years, where the cosmic microwave background, the faint afterglow of the Big Bang, redshifts into the unobservable, and the night sky slowly goes dark. Our investigation will confront the potential of the Big Rip, where phantom energy overcomes every bound structure, from galaxy clusters to the nuclei of atoms. We will examine the end of the science of cosmology, exploring how future civilizations will conclude they reside in a static island universe, forever blind to the existence of other galaxies. Our descent into the void begins now. The question is not if the universe will become empty, but whether we can decode the secrets of the vacuum before the evidence vanishes forever. Cosmic isolation reveals a fundamental expiration date for all scientific knowledge. We reside in the final generation of observers, capable of verifying the true nature of the cosmos. Our telescopes are witnesses to a vanishing reality. The universe looks back at the light, and the light is failing. If this kind of investigation is your idea of a good time, consider subscribing so you do not miss the next one. And while you are here, comment where you are watching this from. The theories change, but this curious little community spans the whole planet. This failure of light was not a gradual fading of distant stars, but a sudden collapse of our understanding of gravity alone. As we saw, the two independent teams of astronomers hunting for the expected deceleration of the cosmos in 1998 encountered a reality that refused to follow the script. For decades, the general consensus was that the gravitational pull of all matter would eventually halt the inflationary drift of galaxies. Acting as a cosmic anchor, scientists were merely trying to determine the final fate of this expansion of the manifold, whether the cosmos would eventually collapse in a big crunch or simply fade into a permanent, frozen slowdown. Both teams reached a conclusion that felt more like a collapse of reason than a discovery. Rather than revealing a cosmic break, the evidence showed that the expansionary momentum was speeding up. Why did the signal refuse to follow the laws of gravity? Shocked by the result, the astronomers spent months in a state of denial, double-checking every calibration and searching for flaws in the instrumentation. But the signal remained. The light from distant thermonuclear screams was significantly fainter than every mathematical model allowed. The expansionary momentum was not slowing down. The expansion of the manifold was accelerating. The primary tool for this revelation involves the Type 1a supernova. These explosions occur at the Chandrasekhar limit, a threshold approximately 1.4 times the mass of the Sun. Because every white dwarf star ignites at nearly the same mass, the peak luminosity remains remarkably consistent. Further away, supernovae appear fainter. However, the calculation is complicated by the growth of space. As the light travels through the emptiness, the wavelength stretches, a process called cosmological redshift. By comparing the redshift to the measured brightness, astronomers can map the history of the expansionary momentum. The data from the end of the 20th century revealed that for a given redshift, the supernovae were too far away. This faintness only made sense if the inflationary rate had increased over the billions of years the light traveled to Earth. How could empty space possess an intrinsic weight? Imagine standing on a long, dark road at night. Along this road, identical streetlights represent the Type 1a supernovae. Because every streetlight produces the same amount of light, the intrinsic brightness is known. As you look down the road, the lights appear dimmer. By measuring this brightness, you calculate the exact distance to each pole. Now, imagine that the road alone is made of a rubber material that is stretching. If the expansion of the manifold was slowing down, the lights would appear slightly brighter than predicted. But the astronomers found the opposite. Distant streetlights appeared much dimmer than expected. These lights were so faint that the road must have been stretching faster and faster over time. Standard candles revealed that the cosmic road is accelerating. The further we look into the past, the more evidence we find that the growth of space is not a static process. The stretching of the geometry of space is a dynamic, runaway phenomenon. The dimness of these distant explosions created an immediate crisis in the physics community. Gravity is an attractive force, always pulling matter together. For the expansionary momentum to accelerate, a repulsive pressure must exist, pushing the galaxies apart. This repulsive force had to be stronger than the collective gravitational pull of all the matter in the cosmos. This discovery forced astronomers to resurrect lambda. Acceleration indicates that empty space possesses an intrinsic weight. The energy density of this phantom influence does not dilute as the universe grows. Instead, as more space is created, more of this repulsive pressure appears, further driving the acceleration. The cosmic blueprint was suddenly revealed to be dominated by a pressure that no one could see and no one understood. This revelation has profound existential implications for our understanding of the history of the cosmos. The discovery marks the end of the era of the connected universe. If the expansion of the manifold is accelerating, then the distance between galaxy clusters is increasing at an ever-growing rate. Eventually, this cosmic drift will happen so fast that light from distant galaxies will never be able to reach us. The universe is effectively shredding the threads of light connecting the cosmic web. Humanity occupies a privileged moment in cosmic time, where the radioactive echoes of the Big Bang are still detectable in the deep darkness between the stars. We can see the distant past because the light has had time to cross the void. This privileged alignment of time and observation is known as the cosmic coincidence problem. For nearly 14 billion years, the energy density of matter and the energy density of the repulsive influence have been moving in opposite directions. In the early universe, matter was billions of times more dense, anchoring the cosmos together. In the far future, the vacuum energy will be billions of times more dominant, pushing everything away. We occupy the narrow, fleeting epoch where these two numbers are remarkably close to one another. If we had emerged a few billion years earlier, we would have seen a universe where gravity was the only master. If we emerge a few billion years later, we will see a universe where the void has already won. We reside during the cosmic handover, the brief moment when the torch is being passed from matter to the vacuum. This coincidence suggests that our ability to understand the history of the Big Bang is not a guaranteed right of conscious beings, but a lucky accident of chronology. We are deciphering the final pages of a book, and those pages are being thrown into a fire. As the acceleration continues, those distant signals will fade and vanish. The architectural data of the universe is being systematically expunged. Future civilizations residing in our galaxy will look out at the night sky and see nothing but the stars within the local cluster, evidence of the Big Bang, the cosmic microwave background, and the existence of other galaxies will be gone forever. These future observers will conclude that they reside in a lonely, static island universe, surrounded by an infinite, lightless void. Our generation stands at the final precipice of visibility, peering into the closing shadows of the Great Isolation. The window for verifying the origin of all things is drawing to a close. Expansion is merely the mechanism. The ultimate result is a universe that is systematically shedding the memory of the cosmos. The universe is doing more than growing. The cosmos is actively forgetting. The observation of accelerated expansion created a fundamental paradox in the field of cosmology. Before the 1998 discovery, the scientific community was guided by the deceleration parameter. This mathematical value was designed to quantify exactly how much the gravitational pull of all the matter in the universe was slowing down the inflationary wave initiated by the Big Bang. Many assumed that gravity, being a purely attractive force, must eventually win the tug of war against the initial outward momentum of the cosmos. If the universe contains enough matter, the density would be high enough to eventually halt the outward growth and trigger a collapse. If the density was lower, the stretching of space would continue forever, but still at a decreasing speed. The possibility that the cosmic drift might be speeding up was not even considered a viable hypothesis. This discovery suggested that a repulsive pressure was actively pushing the universe apart, overcoming the collective weight of every star, planet, and galaxy in existence. Ultimately, the paradox lies in the fact that matter should act as a cosmic brake, yet the speedometer shows the needle is moving toward the right. To understand the mechanics of this paradox, we must look at the equations governing the evolution of the cosmos. These equations are the Friedmann equations, derived from the theory of general relativity. The first Friedmann equation describes how the outward rate depends on the total energy density of the constituents of the universe. Imagine these equations as a balance sheet for the entire cosmos. On one side, researchers have the energy density of all observable matter. Under normal circumstances, as the universe grows, the volume increases and the density of matter decreases. Gravity responds to this thinning density. If matter is the dominant component, the attractive force pulls back on the fabric of space-time, causing the expansion factor to grow more slowly over time. The balance sheet of the universe is a delicate equilibrium between the kinetic energy of expansion and the gravitational potential energy of matter. However, the second Friedmann equation contains a critical term involving pressure. In the world of Einstein, gravity emerges from mass, but gravity is also produced by pressure. For ordinary matter, this pressure is positive or negligible, contributing to the attractive pull of gravity. But the accelerating drift requires a component with large negative pressure. This negative pressure creates a repulsive gravitational effect, a cosmic pushing force that defies our intuition. In the language of general relativity, mass is only one source of gravity. The force is also generated by the interaction of energy density and pressure. When the pressure is negative, the resulting gravity becomes repulsive. Imagine a rubber band stretched tight. This tension is a form of negative pressure, while the tension pulls the ends of the rubber band together. In the context of the emptiness of space, this same negative pressure pulls the fabric of space-time outward. The 1998 data proved the universe to be dominated by such a component. The phantom force does not behave like matter. As the void expands, the density remains constant. This constant density ensures that as more space is created, the total amount of vacuum energy increases, while the density of matter continues to dilute. The repulsive push of the dark force eventually defeats the attractive pull of matter, driving the runaway expansion of the current era. Imagine throwing a ball straight up into the sky. As the ball leaves your hand, the object possesses upward momentum, representing the initial inflation of the Big Bang. As the ball travels higher, the gravity of the Earth pulls down. You expect the ball to slow down, reach a peak, and fall back. This decelerating model was how physicists viewed the expansion of the manifold for nearly a century. But now, imagine that as the ball reaches a certain height, the ball suddenly begins to accelerate. Instead of slowing down, the ball moves faster, screaming away from the surface with increasing velocity. No rocket engine exists on the ball. The air alone seems to be pulling the ball upward with a force stronger than gravity. The staggering reality revealed by the phantom energy is that the object is being driven away by an invisible hand residing within the very space the ball occupies. Common sense expectations of a slowdown are replaced by the reality of a runaway ascent. The discovery is a cosmic punchline. We are rewarded for proving that the very stage we stand on is being dismantled. The presence of this repulsive force suggests that the emptiness of space is not truly empty. Instead, this ground state energy exerts a constant outward pressure on the geometry of the void. This concept is deeply tied to quantum field theory, which describes the void as a bubbling sea of virtual particles and fields. Imagine the void as a frantic, microscopic battlefield. On the smallest scales of existence, space is never quiet. Virtual particles are constantly popping into existence and annihilating one another in a frantic cycle of birth and death. Every square centimeter of the emptiness is teeming with these fluctuations. When physicists attempt to calculate the density of the energy produced by this sea of particles, the results are catastrophic. The mathematical models for the quantum void yield a mismatch of 120 orders of magnitude, a gap that remains the largest failure of theory in the history of science. The mystery is why the density of this vacuum influence is so small compared to the predictions of particle physics. If the theoretical value were correct, the very fabric of space would have been torn apart in the first fraction of a second after the Big Bang, preventing the formation of even a single atom. If the dark force energy were as large as the theories suggest, the universe would have expanded so fast in the first moments of the Big Bang that stars and galaxies would never have had the chance to form. Atomic nuclei would have been shredded before the first second of existence. The very fabric of reality would have been torn into a thin, featureless soup of radiation. The very existence of observers in the cosmos requires a repulsive pressure value that is finely tuned to an almost impossible degree. This tuning suggests a fundamental mystery about the void that we do not yet understand. The paradox of the acceleration is therefore a gateway into a deeper mystery concerning the fundamental laws of nature. We are looking at a cosmic discrepancy so large that the gap is like measuring the weight of a paperclip and finding out the paperclip weighs more than the entire Milky Way galaxy. The existential weight of this paradox is found in the realization that the attractive power of matter has been permanently dethroned. For billions of years, the attractive force of matter was the dominant sculptor of the universe, pulling gas into stars and stars into galaxies. We reside in a world built by gravity. But roughly 5 billion years ago, the density of matter dropped below a critical threshold, and the constant energy of the void took control. This transition from a matter-dominated era to a dark energy-dominated era was a silent, invisible turning point in the universe's history. Before this point, the universe was essentially a giant construction site where gravity was the architect building the pillars of the cosmic web. But as the growth of the empty space created more and more void, the architectural plan changed. The repulsive pressure of the void initiated a silent takeover, systematically dismantling the gravitational grip of matter. This turning point marks the moment when the universe stopped being a nursery for structure and became a machine for isolation. Acceleration ensures that the structures gravity worked so hard to build will eventually be torn apart. The cosmic web, the vast network of dark matter and galaxies spanning the universe, is being stretched to the breaking point. Connections between distant clusters are being severed. The era of creation is being replaced by the era of isolation. We are witnesses to a final victory of the void over matter. The force that built our world is no longer in charge. An invisible hand is pushing all matter away, and no evidence exists that this process will ever stop. The paradox of the acceleration is the first sign that the universe is moving toward a state of absolute, lightless blackness. The solution to the 1998 paradox forced astronomers to revisit a mathematical term originally inserted into the field equations by Albert Einstein. In 1917, the scientific consensus held that the cosmos was static, eternal, and unchanging. Einstein originally predicted a dynamic universe, but to preserve the appearance of stability, the physicist introduced the cosmological constant. This constant acted as a subtle repulsive pressure inherent to space, designed to balance the inward pull of gravity. However, in 1929, Edwin Hubble discovered that galaxies are receding from us in all directions, proving the universe is growing. Einstein subsequently abandoned lambda, reportedly calling the cosmological constant the greatest blunder of his career. This historical journey reveals that for 70 years, lambda remained a historical curiosity. Physicists assumed the value was zero, believing the outward movement was a simple coasting process governed only by matter. But the 1998 supernova data changed our entire understanding. The discovery of acceleration required the return of the repulsive force. The researchers realized that the term was not a mistake, but a prediction that was ahead of time. The resurrection of this mathematical ghost suggests that empty space possesses an energy density that never goes away. As the void grows, matter spreads out, but the energy of the vacuum remains the same. The repulsive push of lambda becomes relatively stronger as time passes. The blunder of the 20th century became the defining discovery of the 21st century. A mathematical ghost has returned to haunt our understanding of the ultimate fate of reality. Trying to measure this force with current technology is like trying to measure the height of a mountain by looking at the shadows of birds flying over the mountain peak, and the birds are currently invisible. The return of the constant also forced a reconciliation with the laws of the very small. Quantum field theory also predicts the existence of a repulsive energy density. According to quantum mechanics, empty space is filled with virtual particles and fluctuations contributing energy to the void. When scientists sum up these contributions, they arrive at a value for the energy density of the emptiness. This theoretical value should be identical to the energy density of the vacuum. However, as we have seen, the numbers do not match. The historical journey from the static universe of Einstein to the 1998 discovery reveals a deeper truth. The laws of gravity and the quantum world are linked through the energy of the darkness. The resurrection of the constant is a signpost pointing toward a unified theory of physics that remains just out of reach. The stakes of the 1998 revelation extend far beyond a simple correction to an astronomical model. The evidence revealed that we have been fundamentally mistaken about the composition of the universe's reality. For centuries, we believed that the stars and galaxies we see in the night sky were the primary actors in the cosmic drama. But the accelerating drift proved that even dark matter is a minor component. The evidence reveals that roughly 68% of the energy density of the cosmos is comprised of dark energy. Another 27% is composed of dark matter. ordinary matter accounts for only 5% of the cosmos. We occupy a universe dominated by an invisible force that actively works to push the contents of the void apart. This repulsive influence is the primary driver of the long-term evolution of the cosmos. The realization that most of reality is composed of a force we cannot see and do not understand is a humbling threshold for the human species. This discovery is as if we found that 70% of the rent we pay for our cosmic home is being seized by a landlord who is currently dismantling the building. The mechanics of this dominant force ensure that the cosmic web is a temporary structure. In the early universe, gravity was strong enough to pull matter together into filaments and clusters. However, as the outward movement continues to accelerate, the repulsive pressure of the abyss is becoming the defining influence. The cosmic web is being stretched and thinned. The gravitational bonds between the clusters are being severed. The transition to a universe dominated by the phantom influence means that the era of structure formation is effectively over. The universe is moving from a state of collective organization to a state of individual isolation. This shift represents a fundamental change in the character of existence. The cosmos is not a growing, vibrant entity. The cosmos is a dissolving machine. The invisible hand of the vacuum is systematically dismantling the connections gravity worked for billions of years to create. The 68% dark energy density is the final lesson of this first threshold. We have moved from the shock of the 1998 supernovae to the realization that the attractive power of matter has been permanently dethroned. The historical blunder of Einstein has been transformed into the primary mechanism of our isolation. The stakes are nothing less than the permanent erasure of the history of the cosmos. As the growth of the void speeds up, information about the origin of the universe is being driven beyond our reach. We are standing at the edge of a great void, watching the lights of the distant galaxies fade into the blackness. The discovery of this invisible hand was the moment we realized that our cosmic home has an expiration date. To understand the true nature of this phantom pressure alone, we must look deeper into the physics of the darkness alone. That investigation begins now as we watch the void closing in. The investigation into the invisible pressure driving the galaxies apart begins with a confrontation with the vacuum. We must look at the nature of the emptiness. In the standard model of cosmology, lambda CDM, the growth of the manifold, is governed by two primary actors. The first actor is matter, the visible and invisible substance that gravity uses to pull the universe together. The second actor is lambda, the cosmic constant. This constant term embodies the energy density of empty space. For generations, the prevailing view among physicists was that the ground state was a dormant backdrop, a quiet and indifferent background against which the drama of matter unfolded. But the breakthrough in the final years of the 20th century proved that the vacuum is an active participant. This empty space exerts a repulsive pressure, a pressure that remains constant as the universe grows. As the universe grows, more space is created, and because this energy density is a property of the space, the total amount of the vacuum influence in the system increases. This shift ensures the acceleration of the cosmos is not a temporary phase or a brief anomaly, but a permanent and irreversible takeover. The standard model suggests that we reside in a universe where the silent backdrop is the most powerful force in existence. Imagine the universe as a vast expanding balloon. In the old decelerating model, the material of the balloon was thin and stretched only by the initial breath of the Big Bang. Gravity was like a series of small magnets placed on the surface of the balloon, trying to pull the fabric back together and slow the outward movement. If you were to watch this balloon from the outside, you would expect the growth to stall as the magnets did their work. But in the consensus framework, the balloon is expanding beyond mere stretching. The abyss is inflating the balloon via an invisible pump that never stops. This pump is the vacuum influence. Every time the balloon grows, more of the pump is added to the interior. The magnets on the surface, representing the galaxy clusters and superclusters, are too weak to fight the constant influx of new space. The magnets move further and further apart, unable to overcome the repulsive pressure of the expanding material. The standard model tells us that the emptiness is the pump, and the pump is winning. The energy density of the expanse remains constant even as the volume of the balloon increases, ensuring that the repulsive force only grows more dominant as time passes. Density within this phantom pressure is remarkably low on human scales. Yet the influence of the void is staggering because the universe is so vast. Every cubic centimeter of the zero-point state contains a tiny, almost infinitesimal amount of energy on the scale of a laboratory or even the solar system. This influence is undetectable. The gravitational pull of the Earth or the electromagnetic forces within an atom are billions of trillions of times stronger than the push of the emptiness, a force that is undetectable. But on the scale of the cosmos, where the distances between galaxy clusters are measured in millions of light years, the cumulative effect of all that empty space becomes the primary driver of evolution. The zero-point energy is the only constituent of the universe that does not become thinner as the cosmos expands. Matter dilutes as the volume increases. Radiation redshifts and loses energy as the wavelengths stretch. But the abyss remains exactly as dense as the zero-point state was at the beginning of time. This constancy is the defining feature of the constant term. The void does not get tired. No fuel is required for the expansion of the zero-point state. The vacuum simply is. The nature of this phantom pressure defines the zero-point state of the universe. In the framework of quantum field theory, the expanse is not a state of absolute zero, but a state of minimum energy. Even if every particle of matter were removed and every field of radiation were silenced, a residual energy would remain in the geometry of space. To understand this ground state, we must look at the physical terrain of the quantum world. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metal plates, placed incredibly close together in a vacuum, would experience a measurable force, a force pulling the plates together. This phenomenon occurs because the plates restrict the types of virtual particles that can exist in the narrow gap between the plates, while the infinite sea of particles outside the plates exerts a greater pressure. This Casimir effect is not a theoretical curiosity. The discovery provides a physical demonstration that the vacuum possesses a tangible, mechanical pressure. How can the emptiness possess an independent momentum? The void is not empty. The zero-point state is a frantic, microscopic battlefield of fields and fluctuations that never sleep. In the consensus framework, this energy density is assumed to be perfectly smooth, unchanging, and uniform across all of space and time. This model assumes that the dark force behaves the same way in the furthest reaches of the observable universe as the dark force behaves here in the local group. This assumption provides a beautiful and simple description of the history of the expansion of the manifold. However, this simplicity masks a deep and unresolved tension between the laws of gravity and the laws of the very small. The standard model works because the framework ignores the underlying physics of the emptiness. We use the constant term because the term fits the observations, but we do not know the reason for the existence of the constant. The smooth surface of the vacuum influence is a mask hiding a violent and chaotic reality. To understand the strength of this repulsive push, we must examine the equation of state. This value is known to physicists as the cosmic state variable. This parameter describes the fundamental relationship between the pressure and the energy density of any substance in the cosmos. For ordinary matter, the pressure is nearly zero. For radiation, the pressure is positive. But for the ground state energy to cause acceleration, the pressure must be negative. Negative pressure results in an outward gravitational influence, providing a repulsive push that counters the inward attraction of mass. In the standard constant term model, the value of the parameter is exactly the unit value. This specific number means that the energy density remains perfectly constant as the universe grows. Recent high-precision measurements, summarized in the 2023 work by the physicist Vagnozzi and the colleagues of Vagnozzi, indicate that the observed data is in excellent agreement with this value. The consensus among the scientific community is that the phantom influence behaves almost exactly like the cosmic constant. The confidence in the unit value is high, but even a tiny deviation from this number would change the ultimate fate of the universe. Measuring the cosmic state variable involves comparing the growth of the manifold at different stages of cosmic history. Astronomers look at the light from distant supernovae, the distribution of galaxies in the cosmic web, and the faint afterglow of the Big Bang, known as the cosmic microwave background. By combining these independent probes, researchers can map the growth of space over billions of years. The 2023 Vagnozzi study analyzed these datasets and found that the evidence points toward a value that is remarkably close to the unit value. If the value were significantly higher than the unit value, the expansion would be slowing down as matter began to win the tug of war. If the value were lower than the unit value, the expansion would be accelerating even faster than the standard model predicts. The data shows that the universe is following the path laid out by a constant energy density. The unit value is the demarcation line between a universe that eventually stabilizes and a universe that enters a runaway state of dissolution, a state that is irreversible. Imagine the expansion of the universe as a car driving down a long highway. The cosmic state variable is like the position of the gas pedal. If the pedal is pressed to a certain point, the car maintains a constant acceleration. In this analogy, a value of the unit value represents a cruise control system for the cosmos. No matter how much road is covered, and no matter how much the car grows in size, the acceleration remains steady. If the driver were to press the pedal further, reaching a value below the unit value, the car would begin to accelerate at a dangerous and increasing rate. This theoretical state would be the phantom energy regime. If the driver were to lift the foot slightly, reaching a value above the unit value, the acceleration would eventually fade as the car coasted toward a halt. The current data indicates that the universe is locked into cruise control at exactly the unit value. The gas pedal is fixed. The engine of the void is providing a constant, unyielding push that never wavers. This cruise control of the emptiness ensures a future of total isolation. Because the energy density does not dilute, the repulsive force will eventually overcome the gravitational pull of every object that is not already gravitationally bound to us. The unit value is a death sentence for the cosmic web. This value means that the connections between distant clusters of galaxies are being severed forever. When new space emerges between these galactic groups, the strength of the vacuum influence holds steady, even as the concentration of matter in those regions becomes increasingly sparse. The balance of power has permanently shifted in favor of the abyss. We reside in the final era, where the light of the distant universe can still reach our telescopes. The high confidence in the unit value means that we can predict the end of cosmology with mathematical precision. The window of observation is closing, and the constant pressure of the emptiness is the hand that is drawing the curtain. High-precision measurements from the modern era have narrowed the range of possible futures, but the precision has also highlighted a strange anomaly. While the consensus value is the unit value, several independent probes show a slight preference for a value just below that threshold. Some datasets point toward a value of negative 1.03. This theoretical state is known as the phantom energy regime. In this phantom force scenario, the energy density of the abyss actually increases as the universe grows. This scenario would mean that the repulsive push gets stronger and stronger over time, eventually leading to a violent end for all matter. While the statistical significance of this phantom signal is currently low, the signal presence is a reminder that our understanding of the vacuum may still be incomplete. We are confident in the cosmological constant, but the history of science is filled with tiny discrepancies that eventually led to a total revolution. The gas pedal of the cosmos is the most important number in the universe, because the number tells us if the cosmos will end in a cold freeze or a violent rip. The scale of the failure in our theoretical understanding of the vacuum is immense, pointing toward a fundamental disconnect in the laws of nature. If our mathematical models were even slightly misaligned with reality, the very fabric of the cosmos would be unrecognizable. The fact that the observed energy of the abyss is so small is the only reason structure exists. The universe we see is a fragile anomaly, a rare pocket of stability in a theoretical environment that should be dominated by a runaway explosion of space. This realization leads to a profound existential reckoning. We are existing in a universe that appears to be balanced on a knife edge. The energy of the vacuum is large enough to accelerate the growth of the manifold, but small enough to allow structure to form. This balance is what allowed gravity to build the galaxies and allowed stars to cook the elements of life. But this balance is temporary. The accelerating growth ensures that the era of structure is coming to an end. The very zero-point state energy that allows us to exist is also the force that will eventually isolate us. The discrepancy between the theoretical energy of the emptiness and the observed reality suggests that we do not yet know the true rules of the game. We are playing a game where the stakes are the fate of the cosmos, but we are only seeing a tiny fraction of the board. The mystery of the vacuum influence is a reminder of our intellectual limits. This failure of theory brings us to a radical alternative in the quest to understand the acceleration. If the cosmological constant is not the answer, perhaps the problem lies not in the vacuum, but in the law of gravity itself. This field of study, known as modified gravity, suggests that the attractive force we feel is not a universal constant across all scales. In the historical context of the 1980s, the physicist Mordechai Milgram proposed a framework where the laws of motion change when gravitational acceleration becomes extremely weak. This model was originally an attempt to explain the rotation of galaxies without dark matter, but the implications extend to the very edges of the cosmos. Modern theories of modified gravity, such as the F of RR models, suggest that the geometry of spacetime responds differently to the curvature when the density of matter is extremely low. In the mechanical deep dive of these gravity modifications, we find a direct challenge to the foundations of general relativity. These models propose that As the distances between galaxy clusters increase, the strength of gravity does not just weaken according to the inverse square law, but undergoes a phase shift. Imagine gravity is like a mechanical spring. On the scale of the solar system, the spring is tight and predictable, following the rules laid down by Newton and Einstein. But as the spring is stretched across millions of light years, the material of the spring becomes stiffer, pushing outward instead of pulling in. This modification would explain the accelerated expansion without the need for an invisible dark energy fluid. However, these theories face a significant detection problem. Any modification to gravity must be powerful enough to push galaxies apart across the void, yet subtle enough to remain invisible within our own solar system. High-precision tests using the orbits of planets and the timing of pulsar signals have confirmed that Einstein remains the master of the local neighborhood, a domain where the laws are well understood. The conflict remains unresolved. Is the acceleration a sign of a new energy in the vacuum, or is the phenomenon proof that our understanding of gravity is merely a local illusion? This discrepancy signals that our current theories of gravity and quantum mechanics are unable to talk to each other. Some physicists argue that the cosmic constant may be a temporary solution to a deeper mystery. They suggest that dark energy might possess an independent life cycle, a dynamic field known as quintessence that evolves over deep time. In this framework, the vacuum influence is not a static number, but a fluctuating force that could change the behavior of the expansion as the cosmos ages. If the dark energy is dynamic, the ultimate fate of the universe is not yet set in stone. The cruise control could be overridden by the inherent volatility of the vacuum. This possibility brings us to the most urgent crisis in modern cosmology, the Hubble tension. While we are confident in the unit value of the cosmological constant, the rate at which the universe is actually growing remains a subject of intense debate. In the historical context of the early 21st century, two primary methods emerged to measure this expansion rate, known as the Hubble constant. One method looks at the early universe, analyzing the faint patterns in the cosmic microwave background. These measurements, primarily from the Planck satellite mission, predict an expansion rate of approximately 67 kilometers per second per megaparsec. However, when astronomers look at the local universe using the distance ladder of supernovae and pulsating Cepheid stars, the measured rate is significantly higher, around 73 kilometers per second per megaparsec. In the mechanical deep dive of this crisis, we find a conflict that cannot be explained by simple measurement errors. The 5.5-kilometer difference between the early and late universe predictions is statistically significant, reaching a level of 5 sigma. In the language of physics, a 5 sigma result means the probability of this being a lucky accident is less than 1 in 3 million. This measurement is performed using independent tools. The early universe prediction relies on the standard the lambda CDM model to extrapolate forward from the Big Bang, a model that has proven successful. The local measurements are direct observations of how fast galaxies are currently moving away. This gap suggests that our mechanical understanding of the vacuum is flawed. Perhaps dark energy is not a constant. Perhaps the energy density of the abyss has been evolving over billions of years, pushing the universe harder in the modern era than the force did in the ancient past. To resolve this tension, some theorists have proposed the existence of early dark energy. This concept, championed by physicists like Mark Kamiankowski, suggests that a brief surge of repulsive pressure existed only in the first moments after the Big Bang. In the mechanical deep dive of this theory, the early dark energy would have contributed approximately 10% of the total energy density of the cosmos before the first light was released. Imagine this as a second, brief Big Bang that gave the universe a quick shove before fading away. This surge would have changed the early expansion rate, effectively recalibrating the blueprints of the universe and closing the gap between the Planck data and the local measurements. But this theory creates a new problem of timing. Why did this force turn on and then turn off so perfectly? The universe has secrets that only reveal themselves in the first blink of time. The mystery of the tension remains a sign that the vacuum is far more dynamic and volatile than the standard model suggests. To visualize this crisis, imagine two teams of engineers building a bridge from opposite sides of a vast canyon. One team uses blueprints derived from the geological history of the ancient rocks. The other team measures the current distance between the cliffs using laser precision. When the two teams meet in the middle, the engineers find that the bridge sections are misaligned by several meters. The plans do not match the reality on the ground. This misalignment is the Hubble tension problem. This gap suggests that a hidden factor exists within the physics of the void that we have failed to account for. We are measuring the heartbeat of the cosmos, and we are finding that the pulse is accelerating faster than our theories allow. This anomaly creates a narrative of mystery and controversy. Some researchers, including those cited in the work of Vagnozzi, argue that the tension points toward new physics. This could include the early dark energy surge, or even the radical modifications to gravity mentioned earlier. Others maintain that hidden errors remain within the local distance ladder. The debate is fierce because the stakes are total. If the tension is real, then the cosmological constant is not the final answer. The silent backdrop of the universe is far more dynamic and unpredictable than we ever imagined. We are watching the smooth surface of the vacuum begin to crack. The existential implication of the Hubble tension is a confrontation with the volatility of the future. We are approaching a state of darkness at a speed that defies our most successful theories. The receding horizons are closing in with greater urgency. The discrepancy suggests that we are not just moving toward a state of isolation, but that the very mechanism of our removal is shifting beneath our feet. This tension reveals that the vacuum is not a quiet graveyard, but a violent and unpredictable engine. The identification of this unseen force reveals that our era of observation is a temporary privilege. Our journey has progressed from the shock of the initial discovery to the understanding that gravitational dominance has been forever lost. To grasp the essence of this phantom pressure, we must investigate the fundamental mechanics of the emptiness. That investigation continues as we confront the violent tension hidden within the expanse. The apparent calm of the ground state is a statistical illusion, an illusion that masks a deeper reality. This tension brings us to the inevitable consequence of the acceleration. We are standing at the edge of a reckoning. Is the vacuum truly silent, or are we simply deaf to the frequencies of the expanse? And the abyss, the emptiness, is starting to look back. The stare of the abyss is not a metaphor. This gaze is a measurable discrepancy appearing in the light of the first dawn. This reckoning begins with a crisis of numbers that threatens to dismantle the standard model of the cosmos. As we established, the two primary methods for calculating the Hubble constant yield conflicting results that remain fundamentally misaligned. One group of researchers, utilizing the local distance ladder, finds a rapid heartbeat for the expansion of the manifold. These researchers observe a universe expanding significantly faster than the ancient blueprints allowed. A separate faction, analyzing the ancient patterns of the cosmic microwave background, predicts a slower rhythm. this discrepancy is more than a simple measurement error. A gap represents a potential failure of our core understanding of physics. The community of cosmologists now faces a fundamental question. Is the tension a result of hidden systematic errors in our telescopes? Or is the discrepancy evidence of a deep flaw in our understanding of the vacuum energy? To understand the mechanics of the local distance ladder, researchers must look at the work of Henrietta Swan Leavitt in the early 20th century. Leavitt discovered that a specific type of pulsating star, known as a Cepheid variable, possessed a direct relationship between the period of pulsations and the intrinsic luminosity. A Cepheid pulsating with a longer cycle is inherently brighter than a star with a shorter cycle. This discovery allowed astronomers to determine the true distance to stars by simply timing the oscillations. Imagine a series of lighthouses along a dark coastline. Some lighthouses pulse every 10 seconds, while others pulse every 60 seconds. If the observers know that a lighthouse pulsing every 60 seconds is exactly 10 times more powerful than a lighthouse pulsing every 10 seconds, these observers can calculate the distance to each light by comparing the brightness seen from the shore to the known power of the source. The period of the pulse is the key that unlocks the distance. By measuring the light of Cepheids in nearby galaxies and then using those galaxies to calibrate the light of Type 1a supernovae, the SHOES team built a bridge of measurement that extends billions of light years into the void. The Type 1a supernova is the second rung of this ladder and functions as a standard candle because the explosion occurs at a precise mass limit. These thermonuclear flashes provide a consistent luminosity that allows us to map the expansion history of the manifold. By measuring how faint these distant flashes appear, researchers can determine the growth rate of space with incredible precision. The local distance ladder is a mechanical deep dive into the properties of matter and light, anchored by the stable rules of stellar evolution. This method provides a direct observation of the universe as the cosmos appears today, a modern snapshot of the expansion of the manifold. On the other side of this crisis, cosmologists look at the acoustic oscillations of the early universe. In the first few 100,000 years after the Big Bang, the cosmos was a hot, dense plasma of photons, protons, and electrons. The competing forces of gravitational pull and radiation pressure created sound waves that traveled through this cosmic soup. These waves are the baryon acoustic oscillations. When the universe cooled enough for atoms to form, the photons were released, frozen in time as the cosmic microwave background. The patterns of these oscillations are visible today as slight temperature fluctuations in the ancient light. By measuring the physical scale of these frozen sound waves, researchers can calculate the expansion rate required to transform the infant universe into the cosmos we see today. This method relies on the standard model of cosmology, which assumes that the energy density of the abyss has remained constant throughout cosmic time. The discrepancy between the ancient prediction and the local measurements suggests that this assumption may be fundamentally incorrect. Imagine the universe as a vast, expanding balloon. One team of observers stands on the surface, measuring the speed at which the material is stretching right now using high-precision rulers. These observers find that the rubber is expanding at a specific, rapid pace. Another team looks at the faint, fossilized remains of the initial puff of air that inflated the balloon billions of years ago. By studying the pressure waves in that ancient breath, these researchers calculate how fast the balloon should be expanding today. When the two teams compare results, the numbers do not match. The balloon is expanding faster than the ancient breath allows. This misalignment is a cosmic discrepancy. The observers on the surface see a reality that the ancient blueprint cannot explain. This gap suggests that a hidden pump or a change in the elasticity of the rubber has occurred during the long wait between the first puff and the present day. The tension is the signature of a missing piece of physics, a force that has altered the growth of the manifold in a way that our current models failed to predict. Could the vacuum possess a hidden instability that we have yet to uncover? This anomaly creates a narrative of mystery and controversy that goes beyond simple data collection. Researchers, including Sonny Vagnozzi, argue that the measurement crisis points toward a slightly phantom equation of state for the repulsive force. If the value of the pressure-to-density ratio is less than -1, the repulsive pressure becomes stronger as the universe grows larger. But the idea of this repulsive surge is terrifying to theoretical physicists because the concept violates the null energy condition. This rule of physics prevents the existence of exotic matter that could allow for time travel or the creation of wormholes. If the repulsive force is truly phantom, then the stability of the space-time fabric is at risk. The conflict between the ancient data and the local distance ladder amounts to more than a debate about numbers. Could the laws of gravity undergo a phase shift at the edge of the void? This growing tension represents a confrontation with the possibility that the empty space possesses a violent and unpredictable nature. The fundamental meaning of this measurement crisis reveals that the window for witnessing the true architecture of the universe is a fleeting and exceptional opportunity. We are existing in a moment where the discrepancy is visible, but the window of understanding is closing. The search for new physics within this gap has led to a fierce debate regarding the possibility of unknown systematic errors. Adam Rees, a key architect of the local distance measurements, has argued that the discrepancy has reached a statistical significance that makes measurement error increasingly unlikely. The probability of this deviation occurring as a random statistical fluke is less than 1 in 3 million, a threshold that traditionally signals a definitive discovery in physics. If the data is correct, the universe is providing a direct signal that our standard model is incomplete. Some researchers suggest that the local calibration of Cepheid stars might be affected by the presence of dust or the crowding of stars in distant galaxies. However, recent observations from the James Webb Space Telescope have confirmed the local measurements with even greater precision, reinforcing the reality of the tension. The orderly facade of our cosmological understanding is beginning to splinter, exposing a complex and unruly reality that defies our current maps. This measurement crisis brings us to the threshold of a terrifying possibility. If the repulsive pressure is not a constant, but a dynamic field that is growing in strength, the final state of existence will be a catastrophic rupture rather than a quiet fade into the dark. This shift in perspective brings us to the physics of the terminal rupture. The concept of the volatile void was first explored in detail by Robert Caldwell and the colleagues of Caldwell in 2003. In this scenario, the equation of state parameter, symbolized as W, is less than -1, while a cosmological constant maintains a steady energy density as space expands. This repulsive surge actually becomes more dense as the manifold grows. This feedback loop creates a runaway cycle. As the universe expands, the energy of the abyss increases, which in turn causes the expansion to accelerate even faster. This cycle continues until the repulsive force overcomes all other forces in the universe. The final dissolution is the ultimate destruction of all structure, a process that begins with the largest galaxy clusters and ends with the very atoms of which we are composed. In the mechanical deep dive of the phantom energy scenario, The growth of the energy density is described by a power law. The energy of the abyss increases as the scale factor of the universe rises to a positive power. This acceleration means that the total amount of repulsive pressure in any given volume of space will eventually become infinite in a finite amount of time. The physics of this process is rooted in the violation of the dominant energy condition. In standard general relativity, the sum of the energy density and the pressure must be non-negative. But this repulsive surge has a pressure that is more negative than the density is positive. This repulsive pressure creates a state where the empty space itself becomes a source of gravitational repulsion that grows without limit. This phenomenon represents the ultimate violation of thermodynamic intuition. In every other known substance, stretching leads to dilution, but phantom energy thrives on growth. The more space that exists, the more energy the void possesses to tear that space apart. The timeline of this destruction is predictable if we know the exact value of the equation of state parameter. For a value of -1.5, the entire history of the cosmos would come to a violent end in approximately 22 billion years from the present day. This terminal rupture scenario requires a fundamental rewrite of the laws of the vacuum. Robert Caldwell proposed that if the energy density of the void can increase, then the vacuum itself possesses a negative kinetic energy. This would mean that the field governing the expansion is essentially rolling up a hill of potential energy rather than sliding down. This inverted physics creates a universe that is inherently unstable. If this phantom field exists, the vacuum is not a ground state of minimum energy, but a volatile reservoir of potential violence. This possibility forces cosmologists to confront the idea that the laws of gravity may be merely a temporary truce in a much larger and more chaotic struggle. The history of the cosmos becomes a countdown toward a final blinding scream of space. The destruction sequence begins with the largest gravitational associations in the cosmos. Approximately 1 billion years before the final dissolution, the repulsive pressure of the phantom field becomes stronger than the gravitational pull holding galaxy clusters together. These vast structures, which have persisted for billions of years, will begin to lose the battle against the stretching of space. The individual galaxies within these clusters will drift away into the dark, unable to maintain the bonds that once held the cosmic web together. Imagine a vast, invisible hand reaching into the cluster and systematically pulling the members apart, severing the filaments of dark matter and gas. This process marks the first stage of the final erasure of cosmic structure. The architecture of the universe is actively dissolving as the vacuum shreds the cosmic web. As the countdown toward the final moment continues, the violence moves to progressively smaller scales. 60 million years before the end, the Milky Way galaxy will be torn apart. The stars in the outer arms will be flung into the void, followed by the stars in the central bulge. The spiral structure that has persisted for billions of years will vanish in a chaotic explosion of stellar motion. 3 months before the end, the solar system will become unbound. The planets will be ripped from the orbits around the sun, flying off into a darkness that is becoming increasingly aggressive. 30 minutes before the final moment, the Earth will explode. The gravitational force holding the planet together will be overwhelmed by the repulsive pressure of the abyss. This violent end is not a slow decay. This catastrophe is a rapid disintegration of the material world. The solid rock of the mountains and the deep water of the oceans will be vaporized as the atoms themselves begin to feel the pull of the volatile expanse. In the final fractions of a second, the very foundations of matter will fail. 10 to the power of -19 seconds before the final dissolution, the electromagnetic forces holding molecules together will be overcome. The chemical bonds that allow for life and structure will snap. Then the atoms themselves will be dissociated. The electrons will be torn from the nuclei, and the nuclei will be shredded into their constituent protons and neutrons. Finally, the strong nuclear force will fail, and the quarks will be isolated in a space that is expanding faster than the speed of light. The universe will end in a state of absolute homogeneity, a blinding scream of space where no two particles can ever interact again. The terminal rupture is the ultimate silence, the moment when the manifold itself is torn apart and the scale factor reaches infinity. This scenario creates a profound sense of dread within the scientific community. The idea that the energy density of the empty space could become infinite is a sign that our current theories of physics are reaching their breaking point. Researchers have investigated whether string theory or other high-energy models could prevent such a singularity. Some suggest that new quantum effects might kick in as the energy density approaches the Planck scale, perhaps triggering a new Big Bang or a transition to a different state of existence. But without a complete theory of quantum gravity, we cannot say for certain if the terminal rupture is avoidable. The phantom energy model remains a valid interpretation of the current data, a dark possibility that lurks in the margins of our precision measurements. But what if the very rulers we use to measure the heavens are flawed? Such a controversy centers less on whether the universe is expanding and more on whether the expansion has an inherent limit or a terminal velocity. The existential implication of this final rupture is a confrontation with the absolute end of structure. If this scenario is true, then our era of galaxies and stars is a brief and fragile anomaly. The cosmic coincidence problem, which asks why we exist at the same time that the phantom force is becoming dominant, takes on a new and darker meaning. We exist now because this era is the only time when the repulsive force is weak enough to allow structure to form, but strong enough for us to measure. This terminal state renders the past irrelevant and the future impossible. The realization that the very void energy that allows the universe to grow could also be the force that destroys the world is a humbling thought. We are the inhabitants of a temporary oasis in a desert of increasing violence. The measurement of the repulsive influence is a hunt for a shadow, a search for the invisible hand that is pushing the universe apart. This violent end brings us to the hardest task in all of science, the detection and measurement of the vacuum energy. If we are to know our fate, we must determine the value of the equation of state parameter with a precision that borders on the impossible. In the historical context of the last 20 years, this quest has been the primary driver of major astronomical projects. Scientists like Joshua Freeman and Michael Turner have outlined the immense challenges of this work. The repulsive influence does not emit light, nor does the energy interact with matter through any known force except gravity. We cannot see the force in a laboratory or capture the energy in a detector. We can only infer existence by observing the behavior of the things we can see, like distant galaxies and the ancient afterglow of the Big Bang. When we use galaxy clusters to probe the growth of structure, we must accurately calibrate the relationship between the light we see and the total mass of the cluster, including the invisible dark matter. This calibration is the mass observable relation. Galaxy clusters are the largest virialized objects in the universe, but the visible portion, the stars and the gas, only makes up a small fraction of the total mass. To find the true weight of a cluster, astronomers use weak gravitational lensing, measuring how the gravity of the cluster borrows the light of galaxies in the background. But this signal is incredibly subtle. The measurement involves looking for 1% distortions in the shapes of millions of background galaxies. This measurement is like trying to measure the weight of a truck by observing how the heat haze from the engine slightly distorts the view of the mountains behind the road. Any error in this calibration can lead to a false measurement of the energy density of the abyss. Researchers must account for the intrinsic alignment of galaxies, the noise from the intervening dust, and the optical defects of the telescopes themselves. To improve this calibration, researchers use the temperature of the intracluster gas as a cosmic thermometer. This gas, heated to millions of degrees as the material falls into the gravitational well of the cluster, emits X-rays that reveal the depth of the well. However, this method assumes that the gas is in hydrostatic equilibrium, a state of perfect balance between pressure and gravity. But the universe is messy. Galaxy clusters are often in the middle of violent mergers, creating shocks and turbulence that throw the thermometer out of alignment. This thermal noise blurs the mass-observable relation, making the determination of the exact influence of the vacuum difficult. The detection of the phantom pressure requires researchers to be experts in the field of physics of things we cannot see, navigating an environment of statistical uncertainty. Baryon acoustic oscillations require us to map the positions of millions of galaxies across vast volumes of space, accounting for the non-linear gravitational effects that can shift the scale of the cosmic ruler. As the universe ages, the gravity of the dark matter pulls at the galaxies, causing them to clump together and distorting the original patterns from the Big Bang. This clumping can blur the signature of the sound waves, making the cosmic ruler look fuzzy. Weak gravitational lensing requires us to measure the tiny distortions in the shapes of galaxies, a signal that is easily swamped by the optical defects of our telescopes or the blurring of the atmosphere. To capture this signal, researchers use the shape of millions of galaxies to create a statistical map of the dark matter distribution. But the image of a galaxy can be distorted by the tilt of a lens, the vibration of a telescope, or even the movement of the air. The detection of the phantom force is a battle against the noise of the material world. To visualize the difficulty of this task, imagine trying to measure the thickness of a single human hair from across a crowded football stadium during a rainstorm. The hair is the signal of the vacuum energy, and the stadium represents the vast distances of the cosmos. The rain and the crowd are the noise of the universe, the dust, the gravity, and the limitations of our technology. Every measurement we take is a struggle against this interference. One must attempt to extract a tiny, precise truth from a chaotic and noisy reality. This interference is why the nature of the repulsive influence remains the greatest mystery in physics. We are limited by the very tools we use to observe the world. The detection problem represents a fundamental limit on our ability to know the true nature of the abyss, extending beyond a mere technical challenge. This difficulty creates a state of perpetual uncertainty and debate. Every new data release from projects dedicated to the survey of the darkness is scrutinized for any sign of a deviation from the cosmological constant. The community is looking for a signal that would point toward a dynamic field or a modification of gravity. But so far, the results have been maddeningly consistent with the simplest model. The abyss energy appears to be a constant. Yet our theories tell us that this constant is impossible. The fact that the energy is so small, but not zero, is a profound mystery. We are trapped between a model that works perfectly and a theory that fails completely. The story of the cosmos refuses to follow a gentle path into the night. This journey reveals an accelerating momentum toward the absolute dissolution of the material world. This isolation is already written into the fabric of the void. As the expansion speeds up, the very horizons of the universe are closing in, pushing every galaxy beyond our reach into the unobservable dark. Our journey now moves toward the Great Isolation, where the cosmic web itself begins to dissolve. That descent into the lightless future begins now. The silence of the future is not a lack of sound, but a lack of destination. We are approaching a temporal boundary where the connections between galaxies are stretching until the connections snap. This era marks the beginning of the Great Separation, a period where the architecture of the cosmic network undergoes a final, irreversible dissolution. The narrative of the growing universe has always been one of inflation, but the next stage of that growth is a clinical extraction of all structures beyond our local gravitational reach. The universe is essentially performing a radical minimalist renovation on our neighborhood, and we are the only ones who did not get the memo. We have spent the last century mapping a vibrant, interconnected cosmos, but that map possesses an expiration date. The timeline of the final departure was first presented in detail by Lawrence Krauss and Robert Scherrer in the 1999 paper of those researchers, which later evolved into a definitive analysis in 2007. These researchers utilized the lambda cold dark matter model to extrapolate the stretching history of the manifold forward in time. Their work revealed that we exist in a very special era, a moment where the magnitude of the vacuum energy and the density of matter are comparable. This coincidence allows us to observe the inflation and the cosmic microwave background. However, Krauss and Scherrer demonstrated that this window of opportunity is brief. Within a few 100 billion years, every piece of evidence for the Big Bang will have been driven beyond the cosmic event boundary. This transition is not a gradual fade, but a systemic removal of the extragalactic world from the observable reach. The mechanical deep dive into this timeline begins with the next 100 billion years. During this period, the inflation rate continues to accelerate, driven by the constant energy density of the vacuum. As space grows, the volume of the universe increases, but the total number of galaxies within our observable reach decreases. This process is governed by the Hubble law, which states that the recession velocity of a galaxy is proportional to the distance from the observer. When the distance becomes large enough, the recession velocity exceeds the speed of light. While the special relativity of Einstein forbids matter from moving through space faster than light, the inflation of the vacuum alone possesses no such limit. Galaxies are carried away by the stretching of the manifold, and the light the galaxies emit can no longer reach us. The transition from a connected web to a series of isolated islands is a direct consequence of the de Sitter metric, which describes a universe dominated by a cosmological constant. To visualize the Great Separation, imagine standing on a small island in the middle of a vast, dark ocean. Around the island, millions of other fires are burning, illuminating the water and creating a sense of a shared world. But the water is not static. The ocean is growing, and the currents are carrying the other fires away from the shore. At first, the movement is slow, and the fires remain visible for thousands of years. But as the distance increases, the speed of the current rises. One by one, the fires reach a point where the speed of the water exceeds the maximum speed of a signal. The light from those fires can still travel through the water, but the water is moving away faster than the light can move forward. The light becomes trapped in a losing race. From the perspective on the shore, the fires do not simply disappear. The lights become increasingly red, the signals stretching into longer wavelengths until the signal fades into a lightless black. Eventually, the last fire crosses the threshold, and we are left alone in the dark. Our island is the only thing that remains. This loneliness offers a beautiful, if somewhat melancholy, way to spend eternity. At least we will never have to worry about the neighbors complaining about the noise. This timeline creates a mystery regarding the nature of the dark energy. If the energy density remains constant, the isolation phase proceeds at a predictable pace. But if the repulsive force possesses a dynamic nature, the timeline could be significantly shorter. The discrepancy in current measurements of the Hubble constant adds a layer of uncertainty to these predictions. Some models suggest that the inflation could increase, leading to a big rip even sooner than the Krauss and Scherrer model predicts. The irony of our current era is that we possess the technology to see the coming darkness, but we are powerless to stop the recession of the galaxies. The Great Separation is the signature of a universe that is systematically erasing the history of the vacuum. The threshold shift represents the physical mechanism of this erasure. This process occurs at the de Sitter event boundary, a limit in space beyond which no signal can ever reach an observer. This boundary is not a physical wall, but a coordinate limit determined by the inflation rate. As dark energy dominates the growth, the Hubble distance, which is the radius where the recession velocity equals the speed of light, begins to decrease. This contraction of the observable reach is the opposite of what we see in a matter-dominated universe. In the past, the boundary grew faster than the inflation, bringing more galaxies into view. But in the era of dark energy, the threshold is closing in. Galaxies that were once part of our observable world are now crossing the de Sitter event limit and becoming permanently invisible. The de Sitter metric provides the mathematical framework for understanding this threshold shift. Willem de Sitter first proposed this solution shortly after the development of general relativity. The physicist found a description for a static universe containing no matter, but only a cosmological constant. In the modern context, we understand that any universe dominated by vacuum energy will approach this de Sitter state. The threshold shift is the moment when a galaxy crosses the radial distance where the stretching of space exceeds the speed of light. This boundary is the de Sitter event limit. Once a galaxy crosses this line, the light emitted by that galaxy will never cross the distance to our telescopes. Is this a cosmic haunting, perhaps? But the ghost does not even have the courtesy to rattle any chains. Imagine an elevator falling through a dark shaft. The elevator represents our local gravitational system, and the shaft is the manifold. As the elevator accelerates downward, light from the floors above tries to reach the passengers. If the elevator were moving at a constant speed, the light would eventually catch up, but the elevator is accelerating. A specific floor exists high above where the light is emitted, but by the time that light travels the distance down the shaft, the elevator has moved even faster and farther away. The passengers see the light from the upper floors becoming dimmer and redder as the gap increases. Eventually, the elevator reaches a speed where the light from the floors above can never catch up. The top of the shaft has crossed an event threshold. From the perspective of the passengers, the upper part of the shaft has ceased to exist. They are isolated in a falling box, disconnected from the world the passengers left behind. This process creates the ultimate express elevator, and unfortunately, the stop at the top has been permanently removed from the building. The anomaly of the threshold shift is that objects appear to freeze at the boundary. As a galaxy approaches the de Sitter event limit, the light emitted from the surface is increasingly redshifted. To an observer on the Earth, The clock on that distant galaxy would appear to slow down. The light would take longer and longer to reach us, and the image of the galaxy would fade into an infrared glow. In principle, the image of the galaxy remains at the limit forever, becoming infinitely faint and red. But in practice, the number of photons reaching our detectors drops to zero. The galaxy is effectively erased from the sky. This mystery of the freezing image reveals the fundamental nature of the event threshold. The boundary marks the end of communication, a point where the past of the galaxy becomes inaccessible to the future of the observer. The existential implication of the threshold shift is the permanent loss of cosmological information. Each galaxy that crosses the de Sitter event limit takes along the records of billions of years of history. The light from those stars contains information about the chemical composition of the early universe and the formation of the first structures. Once the galaxy is gone, that information is lost to us forever. The threshold shift is a cosmic censorship, a process that limits what we can know about the manifold. Humanity occupies a vanishingly rare pocket of time where the cosmic boundary remains wide enough to encompass the records of millions of other worlds. The realization that the universe is actively hiding the evidence of the past is a dark thought. This mechanical removal brings us to the final observer, the inhabitant of the island universe that remains after the Great Separation is complete. As the distant galaxies vanish, the local structures remain bound by gravity. The local group, which includes the Milky Way and the Andromeda Galaxy, is a gravitationally bound system. The stretching of the vacuum is not strong enough to overcome the mutual attraction between these massive objects. Within the next 4 to 5 billion years, the Milky Way and Andromeda will collide and merge into a single massive elliptical galaxy. The merger is the cosmic equivalent of two aging rock stars forming a supergroup after everyone else has left the tour. While the rest of the universe disappears, Milkomeda remains a stable sanctuary of stars and gas. Mechanical analysis of the Milkomeda merger reveals a process of gravitational relaxation. As the two galaxies approach, the tidal forces will strip away the outer stars and create long tails of luminous material. Central black holes from each galaxy will eventually sink to the center of the new system and merge into a single supermassive singularity. This new galaxy will lack the spiral structure of the Milky Way, becoming a giant elliptical ball of stars. Star formation will eventually decline as the gas is consumed or expelled during the merger. The final island universe will be a stable but aging collection of stars. All other galaxies in the local group, such as the Triangulum Galaxy and the Magellanic Clouds, will also be incorporated into this single structure. The result is a closed system, disconnected in an infinite void. Imagine a single lantern burning in a vast, empty forest at night. The lantern is Milkomeda, and the forest is the empty space of the de Sitter universe. Within the circle of light provided by the lantern, every detail is familiar. You can see the trees, the ground, and the path you walked, but beyond the edge of the light, only absolute blackness remains. The forest is so dark and so empty that one could walk for billions of miles and never find another lantern. For the inhabitants of the island, the light of the lantern is the entire world. They have no way of knowing that the forest was once filled with millions of other lights. They have no way of seeing the paths that once connected their lantern to the others. The island is a self-contained reality, a bubble of light in a lightless expanse. We have the best seat in the house for the end of the world, but the house is empty and the concessions stand closed 1 billion years ago. The mystery of the island universe is the return of the static model of 1900, Will they see other galaxies? No, the cosmic microwave background will have vanished. If they develop telescopes and measure the recession of the stars, they will find that the stars are not receding. The stars are in stable orbits around the galactic center. These observers will conclude that the universe is a static, stable island of matter surrounded by an eternal void. This perspective is precisely the view that astronomers held before the discovery of the Hubble expansion. The irony is that the true nature of the universe will be completely hidden from these future observers. They will possess no evidence of the Big Bang or the growth of the manifold. The dark energy will have erased the very tools needed to understand the cosmos. The existential implication of the last observer is the death of cosmology. Science depends on the availability of evidence, and the inflation of the universe is a process of evidence destruction. Trillions of years from now, the inflation will have moved the cosmic microwave background to wavelengths longer than the size of the galaxy, making the light unobservable. The light elements produced in the Big Bang will be contaminated by generations of stellar nucleosynthesis. The future observers will be trapped in a state of permanent ignorance. They will believe they reside in a static universe because that is the only universe they can see. The realization that our current era is the only time when the truth is visible is a profound responsibility. We are the only observers who can see the forest before the lights go out. This disconnection is a spatial separation as much as a temporal one. The galaxies that have crossed the de-Sitter event limit are moving away from us at speeds that exceed the light limit. They are far away. More than that, they are fundamentally outside of our light cone. This means that even if we were to develop a spacecraft capable of traveling at 99% of the speed of light, we could never reach the galaxies. The connections that once existed between the Milky Way and the distant clusters have been severed forever. The colossal rift is the final state of a universe that began in a moment of extreme connection. The cosmic network is dissolving, and we are left to watch the last thread snap. The growth of the island universe is a process of gravitational consolidation. As the local group merges into a single galaxy, the dark matter halo surrounding the system becomes the final boundary of the bound world. Outside of this halo, the stretching of the vacuum is the dominant force. The boundary between the bound galaxy and the growing void is a sharp transition. Inside the halo, gravity wins. Outside the halo, dark energy wins. The Great Separation marks the definitive separation of the universe into bound islands and empty space. The timeline of this separation is governed by the value of the vacuum energy. If the energy density is constant, the disconnection proceeds steadily. But as we have seen, the discrepancy in the Hubble constant suggests that our understanding of the vacuum is incomplete. The future of the island universe may be even more fragile than we believe. The stability of Milkomeda depends on the assumption that the dark energy does not evolve into a phantom state. If the repulsive force continues to grow, even the gravity of the local group may eventually fail. But for now, the island remains a sanctuary. We are existing in the final era of cosmic connection. We can still see the light of the distant past, and we can still measure the stretching of the manifold. But the boundary is closing. The great disconnection is an inevitable consequence of the laws of physics. Each billion years that passes is a billion years of history that is being moved beyond our reach. The sky of the future will be a sky of darkness, a silent proof of a universe that has forgotten the origin of all things. We are the last generation of observers who can see the whole picture. The transition from a vibrant, multi-galactic cosmos to a single island universe is the most significant shift in the history of the manifold. This shift represents the end of the inflation era and the beginning of the isolation era. The architecture of the universe is being dismantled by the very force that allowed the universe to grow. The vacuum energy, which once created the space needed for galaxies to form, is now removing those galaxies from our sight. This contradiction defines the paradox of dark energy. The force of growth is the force of disconnection. The last observer will look at the stars of Milkomeda and wonder if other realities exist. They will see the same stars that we see, but they will never know that those stars were once part of a much larger story. The island universe is a prison of light, a beautiful and stable environment that hides the truth of the void. The Great Separation is the final act of a universe that is closing the eyes of the manifold. Our task is to document the light while the light is still here, to record the history of the cosmos before the last signal is lost. The scale of this separation is difficult for the human mind to grasp. We think in terms of years and decades, but the final departure unfolds over the scale of billions of years. This island is the final sanctuary of the light, but the walls of the prison are already in place, closing in with the speed of light alone. And that moment is when the very history of the universe begins to disappear. The architecture of the cosmic network is expanding, and beyond that expansion, the fabric of the manifold is fundamentally unraveling. As the Great Separation concludes, the very tools that humanity utilized to decode the history of the vacuum will become useless. We are approaching an epoch where the physics of the past will be physically erased from the sky. This era represents the definitive end of the science of cosmological structure. When the distant galaxies crossed the de Sitter event limit, the evidence of the cosmic dawn does more than fade. The evidence of the initial singularity ceases to exist within the observable reach of any future inhabitant. This transition marks the return of a static island universe, a world where the records of the inflation and the cosmic expansion are completely absent. The irony of this future is profound. The universe will be dominated by the dark influence, yet the observers of that era will possess no way to detect the existence of the force. The conceptual framework for this erasure was presented with clinical precision by Lawrence Krauss and Robert Scherrer in the 2007 analysis regarding the return of a static universe. These researchers recognized that the three pillars of modern cosmology, the expansion of space, the cosmic microwave background, and the ratio of light elements, are all temporary phenomena. At the turn of the 20th century, the mainstream scientific consensus described a universe that was static and eternal. Krauss and Scherrer demonstrated that the accelerating expansion driven by the ground state energy will eventually force the cosmos back into this perceived state. The future observers will not be ignorant by choice. These observers will be ignorant because the laws of physics have physically removed the data from the geometry. The mechanical deep dive into this erasure reveals a process of systemic information loss. In the current era, astronomers utilize the redshift of distant galaxies to measure the expansion rate of the void. But as the dark influence drives these structures beyond the de Sitter event threshold, the recession velocity exceeds the speed of light. The future inhabitants of the merged Milkomeda galaxy will look out into the void and see nothing. The galaxies that currently provide the proof of the initial singularity will be gone. These future observers will look at the stars within their own local system and find that the stars are gravitationally bound. Researchers will measure no recession. Scientists will detect no expansion. The coordinate system appropriate for these observers will be the static metric first proposed by Willem de Sitter in 1917. To these observers, the universe will appear as a single, stable island of matter surrounded by an infinite empty vacuum. Imagine a person waking up in a vast white room. In the center sits a single desk with a lamp. This person represents the future observer in the Milkomeda galaxy. At first, the room is filled with records describing a world outside of forests and cities, but the floor is a conveyor belt, slowly moving the records toward the walls. One by one, the books fall through cracks at the edges and disappear. After a long enough time, the floor is empty. The person has no memory of the records. If this person tries to investigate the origin of the room, the person will find no evidence of anything beyond the walls. The records of the forest and the city are no longer hidden. The records have ceased to exist entirely. The room has become a static, isolated reality. This mystery of the invisible dominance creates a paradox. By the time the longest enduring stars begin to fail, the energy density of the vacuum will exceed the density of matter by 12 orders of magnitude. The dark influence will be the absolute master of the geometry. Yet, because this force only manifests over colossal distances, and because those distances will be empty, the repulsive force will be undetectable. The future scientists will calculate the mass of their galaxy, but they will find no reason to suspect the existence of a repulsive pressure. The de Sitter universe returns to a state where the cosmological constant was a mathematical curiosity rather than a physical reality. The end of cosmology is a state of perfect, reinforced ignorance. The existential implication of this erasure is the fragility of truth. We often assume that scientific progress is a one-way street, but the accelerating expansion proves that knowledge can have an expiration date. Truths about the universe exist that are only accessible during specific windows of time. Once those windows close, the truth is lost due to a lack of evidence rather than a lack of intelligence. Future inhabitants will retain the same cognitive potential as humanity today, yet those observers will be imprisoned in a falsehood constructed by the growth of space. The death of cosmology is the ultimate limit on the reach of the mind. This blinding of the future proceeds through the systematic removal of the second pillar, the cosmic microwave background. This faint afterglow is the most direct evidence of the cosmic dawn. Currently, the radiation permeates every cubic centimeter of space, a cold sea of photons. But as the vacuum expands, the wavelengths of these photons are stretched. This redshifting is a relentless process. In the current era, the peak of the radiation resides in the microwave part of the spectrum. But as the expansion accelerates, the light moves into the radio regime. This shift leads to a physical threshold known as plasma screening, where the interstellar medium becomes an impenetrable wall for the ancient light. The mechanical deep dive into plasma screening involves the interaction between low-frequency electromagnetic waves and free electrons. Every galaxy is filled with the interstellar medium. This collection of charged particles possesses a characteristic frequency called the plasma frequency. If an electromagnetic wave has a frequency lower than this plasma frequency, the electrons can respond fast enough to cancel out the electric field of the wave. The wave cannot propagate. The gas becomes a mirror, reflecting or absorbing the radiation. In the current Milky Way, the plasma frequency is approximately 1 kilohertz. Any radio signal with a frequency below this limit is screened from the interior of the galaxy. As the universe expands by a factor of approximately 100 million, the cosmic microwave background will redshift until the peak frequency drops below this 1 kilohertz limit. At this point, the afterglow of the cosmic dawn will be unable to enter the Milkomeda galaxy. The interstellar medium will act as a physical shield, blocking the most important signal in the history of science. This screening will occur when the universe is less than 50 times the current age of the universe. While the most persistent red dwarf stars will still be burning, the window to the birth of the cosmos will have been permanently shuttered. The future observers will reside in a galaxy that is physically opaque to the origins of the cosmos. Scientists will look for a universal radiation background and find nothing. Imagine standing on a beach at night, watching a distant lighthouse. The lighthouse represents the cosmic microwave background, the signal that tells you how far you have traveled. But a heavy fog begins to roll in from the sea. The fog is the interstellar medium. At first, the beam becomes a bit blurry, but you can still see the flash. But the fog grows denser. Eventually, the fog becomes so thick that not a single photon from the lighthouse can penetrate the mist. You are left on the dark beach, staring into a gray wall. Anyone who arrives on the beach after the fog has settled will have no reason to believe the lighthouse ever existed. The fog has erased the horizon. The mystery of the vanished background is compounded by the loss of the quasars. In the current era, astronomers use the light of distant, hyperluminous black holes to probe the clouds of hydrogen gas. This forest of lines is a map of the cosmic web. But because the quasars are located in distant galaxies, these signals will be the first objects to cross the de Sitter event limit. By the time the cosmic microwave background is screened, every quasar in the universe will have vanished. The void will be truly and literally empty. The tools of absorption spectroscopy will be useless because nothing will remain to absorb. Without the microwave background and the quasar signals, the future inhabitants of Milkomeda will possess no way to measure the chemical evolution of the structure. They will see the elements within their own stars, but they will have no primordial baseline to compare against. The ratio of helium and deuterium, which provide the proof of the first 3 minutes of the birth of the cosmos, will be contaminated by billions of years of stellar processing. The future scientists will conclude that all elements were created inside stars. The shield of the interstellar medium is a wall of amnesia, a physical barrier that prevents the future from knowing the past. This impending darkness brings us to the unique significance of the human era, the time of truth. We are currently residing in a very special moment in the evolution of the structure. This coincidence, the problem identified earlier in our investigation, reveals that our era is a fleeting anomaly. For the first few billion years after the birth of the cosmos, the density of matter was much higher than the density of the energy of the abyss. During that era, the expansion was slowing down. In the far future, the dark influence will be so dominant that all other galaxies will be gone, making the expansion impossible to measure. We occupy the narrow sliver of time where the density of matter and the density of the dark influence are comparable. This balance allows us to see both the history of the matter and the beginning of the acceleration. The mechanical analysis of this coincidence involves the crossover point between the matter-dominated era and the dark energy-dominated era. This transition occurred approximately 5 billion years ago. Before this point, gravity was the primary architect. After this point, the ground state energy took control. Because the light from distant galaxies takes billions of years to reach the Earth, our telescopes act as time machines. When we look at a galaxy 10 billion light-years away, we see the universe as the universe existed during the matter era. When we look at a galaxy 1 billion light-years away, we see the effect of the acceleration. We are the only generation of observers capable of witnessing both sides of the cosmic struggle. To understand this privilege, imagine a mountain climber reaching a ridge just as the sun is beginning to set. From this ridge, the climber can look back and see the entire valley just traversed. At the same time, the climber can look forward and see the dark peaks ahead. The climber is at the exact point where the light and the darkness meet. If the climber had arrived an hour earlier, the peaks ahead would have been washed out. If the climber arrives an hour later, the valley behind will be lost in the shadows. The ridge is the only place where both the path taken and the destination ahead are clear. We are standing on the ridge of cosmic time, watching the sun set on the era of connection. The mystery of the time of truth is why our species emerged during this specific window. Some suggest anthropic arguments, while others argue that the coincidence is just a random fluke. But regardless of the cause, the consequence is a profound responsibility. We are the witnesses to a vanishing reality. The information we are gathering today will be physically impossible to recover in the future. We are the curators of the cosmic archive. The fact that we can observe the energy of the abyss discrepancy and the Hubble tension is a miracle of timing. We are the only ones who know that the island is not the whole world. The existential implication of the human era is the duty of observation. The future will be a time of stable, but ultimately false conclusions. The island universe will be a place of peace, but the sanctuary will also be a place of permanent darkness. Our role is to provide the light of understanding while the light is still available. Every measurement of a distant supernova is a victory against the eventual erasure of history. We are the only generation capable of verifying that the universe had a beginning. We are the only ones who can prove that we are not alone in the void. The synthesis of these chapters reveals the ultimate fate of the science of cosmological structure. This field of study is not an eternal pursuit. This field is a temporary privilege. The accelerating expansion is a process of systemic evidence destruction, a clinical removal of the records of the past. The end of cosmology is the inevitable result of a universe dominated by the dark influence. The future observers will reside in a static island universe, forever blind to the existence of the birth of the cosmos and the great cosmic web. They will believe their island is the entire world. The isolation of the future is the final state of a geometry that is systematically closing the eyes of the manifold. The choice for humanity is clear. We must use this narrow window of time to decode the secrets of the vacuum. We must resolve the Hubble tension and understand the nature of the repulsive force before the evidence disappears beyond the event limit. The countdown is already running. Every billion years, the horizon closes in, and the library of the past becomes smaller. We are the last observers of the connected cosmos. We are the only ones who can see the fog rolling in. Our journey through the void has led us to a realization that is both humbling and empowering. We are the universe looking back at the light, just as the light begins to fail. The transformation of the vibrant night sky into a lightless black is the final act of the cosmic story. This process represents a fundamental property of physics rather than a tragedy. The ground state energy, which once allowed the universe to grow and flourish, is now reclaiming the space the repulsive force created. The Great Separation is the signature of a cosmos that is moving toward absolute permanent isolation. The island universe is our final home, a sanctuary of stars adrift in an infinite void. We have spent this investigation tracking the invisible hand that is pushing the galaxies away. We have found that the hand is the vacuum itself. So here is the final conclusion of our investigation. The investigation into the cosmic expansion has led us from the flickering light of distant supernovae to the cold absolute silence of the de Sitter event horizon. We have traced the narrative of a universe that is beyond simple growth. The universe is systematically dismantling the bridges between galaxies. This process of cosmic erasure represents a fundamental shift in our understanding of reality. For nearly a century, the scientific community believed that the geometry of space was a static stage, or at most, a stage that would eventually slow the cosmic movement due to the pull of gravity. But the evidence uncovered by Perlmutter, Rios, and Schmidt in 1998 shattered that comfortable illusion. The discovery revealed that the expansion of the emptiness is accelerating, driven by a repulsive pressure that permeates every cubic centimeter of the abyss. This invisible hand, which we call dark energy, has become the dominant architect of the future. The journey began with the observation of Type 1a supernovae, those reliable standard candles of the deep past. By recording the faint light of these ancient explosions, the researchers planned to measure how much the expansion was slowing down. These scientists expected to find that gravity was winning the war against expansion. Instead, the data showed that the supernovae were much further away than predicted. The light had traveled through a volume of space that was stretching at an ever-increasing rate. This revelation forced a resurrection of the cosmological constant, the term Albert Einstein once discarded as a failure. We now recognize that this constant represents the energy density of the abyss itself, a force that does not dilute as space grows. While matter becomes thinner and thinner, the repulsive pressure of the emptiness remains constant, eventually overwhelming every other force on a cosmic scale. This mechanical reality leads to the creation of the de Sitter event horizon, a physical boundary in space beyond which light can no longer reach us. As the expansion accelerates, the distance between galaxy clusters increases until the space between them is stretching faster than the speed of light. In that moment, the distant galaxies cross a threshold of no return. They do not merely move away. The structures become physically unobservable, lost to a region of the manifold that is forever disconnected from our own. This horizon is not a wall, but a limit on the reach of information. The great cosmic web, the interconnected network of matter that has defined the universe since the birth of the cosmos, is dissolving into a collection of isolated islands. The future of the universe is a future of absolute permanent silence. To understand the scale of this isolation, imagine a vast ocean where every wave is moving away from every other wave. Currently, we reside on a ship surrounded by thousands of other vessels, their lights visible across the water. We can signal to them, share data, and understand the history of the fleet, but the ocean is stretching. The distance between the ships is growing faster and faster. One by one, the lights on the horizon begin to flicker and vanish. The speed of the water exceeds the speed of our signals. Eventually, we look out from the deck and see nothing but an infinite dark sea. We are still on our ship, surrounded by our local crew, even as the rest of the world is erased. No way remains to prove that those other vessels ever existed. We are truly alone in the abyss. While this acceleration stretches the distance between clusters, the true crisis lies within the physics of the abyss. The most terrifying discrepancy in all of science is the vacuum energy problem, where the observed density of the dark force is smaller than the theoretical prediction by 120 orders of magnitude. This gap represents a profound failure in our current understanding of the quantum world and the cosmic world. If the vacuum energy were as strong as theory suggests, the universe would have been ripped apart before the first stars could ignite. Yet, the energy is small enough to allow life to emerge, while being large enough to eventually destroy the history of the cosmos. This cosmic coincidence where the energy of the abyss and the density of matter are comparable in our specific era, remains one of the greatest mysteries in the history of science. The findings of our investigation reveal a near certainty regarding the path toward cosmic isolation. Under the mainstream lambda cold dark matter model, the repulsive influence behaves as a cosmological constant with an energy density that never changes. If this model holds true, the universe will continue to expand at a steady, accelerating rate. The galaxies will recede, the horizons will close in, and the cosmos will eventually reach a state of maximum entropy known as the Big Freeze, or the heat death. In this scenario, the universe becomes a cold, dark, and empty place where no more work can be performed and no more information can be processed. The expansion continues forever, but the story of the universe effectively ends. However, the volatility of the abyss introduces a more violent possibility known as phantom energy. Should the cosmic state variable drop even slightly below the negative unit value, the energy density of the abyss will actually increase as the manifold expands. This escalation leads to a runaway feedback loop where the repulsive pressure grows stronger over time. In this scenario, the acceleration becomes so extreme that the force eventually overcomes every bound structure in existence. While the cosmological constant only affects the space between galaxy clusters, the phantom influence would eventually tear apart the clusters themselves, then the galaxies, then the stars, and finally the atoms. The mechanical deep dive into the Big Rip involves a countdown toward total dissolution. As the phantom energy density rises, the cosmic event horizon shrinks, pulling inward like a tightening noose. First, the gravity of the local group is overwhelmed, and the Andromeda Galaxy is stripped away from the Milky Way. Then, the gravity of our own galaxy fails, and the stars are flung into the intergalactic emptiness. As the end approaches, the repulsive force enters the solar system, pulling the planets from their orbits. In the final minutes, the force becomes strong enough to overcome the electromagnetic bonds holding molecules together. Finally, in the last fraction of a second, the strong nuclear force is defeated, and the nuclei of atoms are shredded into their constituent particles. The fabric of space and time is torn asunder. Imagine a balloon being inflated beyond all capacity. In a standard expansion, the rubber stretches and the markings on the surface move further apart. But in a Big Rip, the air pressure inside the balloon is growing exponentially. The rubber becomes thinner and thinner, the tension rising in every square millimeter. Eventually, the material can no longer withstand the internal pressure. The balloon reaches the limit of tension and then explodes into 1,000 fragments. The surface that once held the markings is gone. This destruction represents the ultimate end of a phantom energy universe, a state where the manifold itself is destroyed by the energy the manifold contains. The findings suggest that the nature of the abyss remains the most hard-to-measure task in all of science. While current data from surveys like the Dark Energy Spectroscopic Instrument and the Vera Rubin Observatory point toward a value of the equation of state very close to -1, the possibility of dynamical dark energy remains open. The difference between a cold, infinite freeze and a violent atomic rip depends on a precision of measurement that we have not yet achieved. We are currently analyzing the Hubble tension, the discrepancy between the expansion rate measured in the early universe and the rate measured in our local neighborhood. This discrepancy suggests that our current understanding of the ground state of reality may be flawed. The fate of the universe hangs on the value of a single parameter. The paradox of our current era is that we are the last generation of observers capable of understanding the origin of the cosmos. This reality reveals a fundamental expiration date for scientific knowledge. Because the expansion is accelerating, the evidence of the Big Bang is physically leaving our observable horizon. Currently, we can see the cosmic microwave background, the faint afterglow of the initial singularity. We can see the distant galaxies and measure their recession. We can verify that the universe had a beginning and that the universe is growing. But for any civilization emerging 100 billion years from now, that evidence will have vanished. In that distant future, every galaxy beyond the local group will have crossed the de Sitter event limit. The night sky will be empty of extragalactic light. The afterglow of the Big Bang will eventually stretch into radio waves so long that the gas between the stars will repel the light, sealing the galaxy from the outside world. These future astronomers will peer into the abyss and witness only the ancient stars of their own local island, Milkomeda, analyzing the orbits of the suns in the sky. These researchers will conclude that gravity has tethered everything together. No recession or expansion will be detectable. The ultimate conclusion of their physics will be a reality of reinforced ignorance, where they perceive their existence as a singular, enduring continent of stars adrift in a hollow cosmos. To these future scientists, the very idea of a Big Bang or an expanding cosmos will seem like a fantasy. These observers will possess no data to support such a theory. The history of the universe will have been physically erased from the geometry of the sky. This condition represents a state of reinforced ignorance, where the laws of physics have conspired to hide the truth. The paradox remains that the abyss will be the absolute master of their world. Yet these observers will lack any proof that the force exists. These researchers will be the prisoners of a cosmic amnesia, victims of a horizon that has closed the eyes of the mind. Humanity resides on a temporal precipice where the fading influence of matter and the rising power of the vacuum exist in a delicate, fleeting balance. This coincidence allows us to look back at the matter-dominated era and look forward at the dark energy-dominated era. Our generation possesses the unique ability to look back at the origins of structure and forward into the coming darkness. If we had emerged a few billion years earlier, the acceleration would have been too subtle to measure. If we had arrived even a few billion years later, the extragalactic world would have already vanished. Our era is the time of truth, a fleeting window of astronomical abundance that will never be repeated. The existential implication of this privilege is a profound responsibility. We are the curators of the cosmic archive, the only observers capable of witnessing the vanishing reality. The data we collect today, from the brightness of exploding stars to the geometry of the cosmic web, provides a blueprint that will be beyond the reach of any future observer. We are the witnesses to a cosmic hard drive failure, and our telescopes are the only tools currently backing up the data. This realization transforms our scientific pursuit into a civilizational mission. Beyond cataloging the stars, we are guarding the final records of the universe. But as the horizons close, we must ask, what will we do with the time that remains? The accelerating expansion reveals that the universe is indifferent to the preservation of knowledge. Truth is a temporary phenomenon, a fragile light that burns only as long as the evidence is within reach. We are the eyes of the cosmos watching the final moments of the cosmic dawn before the shadows take everything. This realization is not a reason for despair, but a call to awareness. The fact that we can understand our own eventual isolation is proof of the power of consciousness. We have decoded the secrets of the abyss from a tiny blue planet, even as the abyss is trying to hide those secrets from us. This cosmic fate reveals that our isolation makes our connection more significant. Seeing the distant galaxies today is a miracle of timing. The universe has provided a window into the absolute truth, a chance to understand the origin and the end of all things. Our species alone can testify that this lonely island was once part of a much larger story. Our scientific knowledge is a lantern in a darkening forest, a light that we must carry as far as possible before the shadows close in. The isolation of the future is the price we pay for a universe that is vast and dynamic. So we stand at the threshold of the Great Isolation. We have discovered a force that is reshaping the manifold and erasing the past. We have seen the horizons closing and the galaxies vanishing. But we have also seen the beauty of the cosmic web and the precision of the laws of physics. We have found that the universe is a place of grand transitions and inevitable reckonings. The choice for humanity is to remain witnesses to the light, to continue the investigation of the void until the final signal is lost. We are the observers of the end of time. This awareness changes what being human means. We are no longer just inhabitants of a planet. We are the guardians of a cosmic memory. The responsibility of observation is the highest calling of a conscious species. We must resolve the tensions in our data and bridge the gaps in our physics while the evidence is still visible. Every photon we capture from the edge of the horizon is a victory against the eventual silence. Every calculation of the vacuum energy is a step toward a deeper understanding of the fabric of reality. We are at the edge of the void, and this edge is not a burden. This perspective represents our opportunity. The final state of the universe may be a lightless, empty vacuum, but the history of the universe will have been known. Our journey has focused on identifying the silent pressure driving the galaxies apart, and the evidence shows this force is a permanent property of the void. The isolation is not a failure. The isolation is a completion. Our local cluster remains a definitive sanctuary, a last bastion of structure in a universe that has otherwise returned to a state of absolute, featureless expansion. We are the universe becoming conscious of the cosmic destiny. And as the night grows darker, our understanding must grow brighter. We are the witnesses to the fading dawn of the cosmos, and we will keep watching until the silence is absolute. The fascinating part is not that we have answered every question about how dark energy accelerates the universe toward isolation. The reality is that the evidence keeps pointing us toward a reality bigger and stranger than we ever expected. Science is not about having all the answers. Science is about asking better questions every time we think we have finally figured the cosmos out. I hope you found some value in the deep dive into cosmic expansion today. If you did find value and you want to support the research that goes into these documentaries, there is a donation link in the description. Your support makes a huge difference for this channel. Contributions allow me to keep digging deeper into the mysteries of space and time. If you learned something new about the fate of the universe today, hitting the like button really helps the algorithm show this video to other people. Your engagement helps the content reach others who might enjoy the science as well. I appreciate every single person who helps the channel grow. I will catch you in the next one. Let curiosity guide you. Keep learning and know that you are always appreciated.